Hey, good. Welcome back from the break. Again, this is the start of week 2, and so this is the second lecture here on Tuesday of week 2. And again, there's only Tuesday and Wednesday this week. And as you might recall, right before the break, we were doing projectile motion. And I'll say it again. Projectile motion at first looks hard, but I'm hopefully getting across to you that it's actually pretty easy calculations. We just do one-dimensional motion twice. And so before the break, we did something tossed straight off horizontally. Let's demonstrate that again, but this time, let's launch something up at an angle first. Watch, let's look at the animation here. And so if I go to the next animation and hit play, we hopefully see kind of the same thing. That is, this red line here is an object that is being tossed, if you will, across the room. It's given an upward and a horizontal velocity. And to illustrate that our components are separate, we put an object with the same vertical, just went straight up to its top and then came down. And also, and again, this is why the animation is here, we have a third object that is going across as if there was no gravity at all. It was just given the same horizontal speed. And so if I go back one step here and watch it again, here I go, hit play. Watch how the vertical is the same as the vertical of what I'll call the real one is the same as the vertical one that has no horizontal motion. And then also the horizontal motion of the real one has the same one as this one we're pretending that is being tossed with no gravity. And so here we go. And so again, the whole point, the whole lesson was to point out that they are treated separately. So when I sit down to do the math here, let me come over here, and I left on the board from the break this whole main idea that the components, that is the X and Y motion, act independently. That's why then when we start doing a calculation and we start asking questions, where is the object or how fast is the object going, it's a two-part question. One is where is it horizontally, and the other is where is it vertically. So this is the same table that has acceleration, velocity, and distance horizontally and then also vertically. And so maybe over here, I'll start off like we kind of had in chapter 2 and 3. But this time I'm going to give the ball a little nudge here, something like this, if you will. And I'll give it a really large speed. Why don't we do this 50 meters per second at 37 degrees. Now, the 37 degrees is not required of you. Remember, I mentioned this in the vector part of our discussion, that this class is kind of that introduction to physics, and we talk about the physical ideas, and one of them is how X and Y are separate, and another one is that vectors have a magnitude and a direction and can always be broken down into their components. But you're not expected to be as far along in your math as trigonometry, but I know about half of you probably are. So if you're familiar with your trigonometry, but more importantly, all of you are familiar with your geometry, this 37 degrees is that 3, 4, 5 perfect triangle. So if I were to throw the ball up at an angle like this of 37 degrees, but give it a speed of 50 meters per second, that means it can be thought of having a horizontal speed of 40 and a vertical speed of 30. And so there's my 3, 4, 5 right triangle. And this brings us back to our discussion on vectors. And so again, I'll give it a little sideways nudge like this. But then I need to realize, wait, 50 is not the speed I want to work with. The 50 is a combination of 40 horizontal and 30 vertical. And so there's our 3, 4, 5 right triangle, or in this case it's multiplied by 10. So instead of 3 it's 30, instead of 4 it's 40, instead of 5 it's 50. Here's why that's important then. And so when I come over here and I start to fill in this chart, maybe the first thing I would do is something like this and say, okay, horizontally it starts off with a speed of 40. And vertically it starts off with a speed of 30. And in this case, I'm going to put an arrowhead up because this one goes up and then down. And so I want to know, is it heading up or is it heading down? So initially it's heading up. But here's the good thing that hopefully you saw at the break is we can calculate these separately. Oh, why don't I go ahead and do the vertical motion first, because that's what we did back in chapters 2 and 3. And so you actually already saw these numbers. You can go back and watch that video again, but you'll see exactly the same numbers. And I think it's worth going through again, and I'll just emphasize that what we said is when something is flying through the air, its acceleration vertically, and then we didn't emphasize vertically last time, so that is what's different here. But its acceleration is 9.8, or very close to 10. So I'll just put a 10 on the board. Okay, but that's its vertical acceleration. Now, since it is going up and then down, it's probably good to also emphasize that the vertical acceleration is not only 10, but it's 10 in the downward direction. See, what that would mean then vertically is it's starting off going up and has an acceleration of down, so that means when it changes by 10, it's a slowing down of 10. So 1 second later, it's going 20. A second after that, it's now going 10. And a second after that, it is now going 0. What that means is vertically it has come to a stop. Up here on the diagram then, this would be its highest point. I lost my little pointer here, but I'll grab this. But we'd be talking about right there. We're at its highest point. It's on its way up and now has stopped. And now it, of course, begins to come down. And so for this chart, I probably need to continue to go to 4 seconds, 5 seconds, and 6 seconds. And of course, if you remember from chapter 2 when we did this, we did say, hey, we needed to make a chart of 6 seconds. And so I will add some more time here to my chart, and keeping in mind that the vertical acceleration is always 10 down, which is why it was slowing down by 10. But now it'll begin to fall, and so as it's going down, it's going to change by 10, but this time speeding up. So 0 goes to 10 down, then it goes to 20 down, and then to 30 down. And so that's the numbers on the vertical column. And also that brings it all the way back to the same height. I proved that to you in chapter 2, but I'll even do it again here. And so again, let's do this calculation. And of course, I'm going to use then this formula again. And I'm going to focus my attention on the average speed. Again, I'll leave this one crossed out because that would only be valid if it started with an initial speed of 0, and this does not. So I wouldn't want to use that one. But if I would say 0 is the position right as I let it go, so I throw it up, then 1 second later, it has gone up a height of 25. In fact, this is exactly the same numbers as the one I did as an example. It was chapter 2, and I forget the exact number. I squished it all up here. But when I started today's lecture, I said, hey, let's look at some ones that are kind of tricky. Looks like it was, no, I don't know if it was 24 or 26. Anyways, but one of the ones I did, and I didn't do the whole chart because I said that I had done that in the previous videos. But notice then that I figured out what the average speed was. So 30 up and 20 up, add them together, that's 50 divided by 2 is 25 for 1 second. This will go 25 up in 1 second. And my next calculation, again using the same equation, I'll just do 1 second at a time. You could have done the whole 2 seconds, but if I just look at this motion, the average here is 15, so it's going to go up another 15. And so if I add 15 onto the 25, I get 40. And again, if I do the same equation right here, you can see I have an average speed for this 1 second of 5. So it's going to go up 5 more, so this is going to be 45. So one of the questions that could be asked here, and I don't even have to do the horizontal, would be how high does this object go? And the answer is 45. Because now it begins to come down, and you can see here coming down, it averages 5, but it's of course down, so 5 taking away is 40. And if you remember back on our lecture in chapter 2 when we did this, I said these numbers here will be exactly the same as these numbers here because it's going to fall at the same rate, 10, as it slowed down, 10. And so it's not a surprise these numbers come out to be the same. But let's just check them. This would come down by 15. That's an average of 15. So 15 away from 40 is 25. And sure enough, matches that one. And then finally, this second here, it has an average speed of 25, so it's going to drop 25 and get back to 0. So coming over to here, this would be the whole motion. And so it looks like it goes up for 3 seconds and then down for 3 seconds. And so after a total of 6 seconds, it's back down on the ground. And so, again, another question that could be asked is how much time did it spend total in the air? And so I would have 6 seconds. So how high did it go? 45. How much time? 6 seconds. What's its speed when it got back to the ground? 30, the same I threw it up as, right? Exact same numbers on this half as in this half. So again, hopefully you're seeing that, hey, yeah, this is pretty easy. You know, I'm simply doing the same numbers that I did in chapter 2. Now, I will say I have to do it twice because I got to do it for the vertical motion and the horizontal motion. So let's do the horizontal motion. That's really the new piece here. But as I tried to point out before the break, and I want to emphasize again, and I'll come over here to this animation, for the horizontal motion, it's as if an object was tossed without gravity. Because remember, X and Y act independently, and gravity pulls it just down. And so gravity starts to give it an acceleration in the Y direction. But in the horizontal direction, it doesn't have any. I'm sure you've seen that many times. You take an object and you drop it. Gravity just pulls it down. It doesn't go like this. There is no X part of gravity. Gravity has 0 acceleration in the X direction. And that's really what is new here, because I have to do these two things twice, but what I have to realize is they do have a different acceleration. The vertical acceleration is the 10, but the horizontal acceleration is a different number. It's 0. And then fortunately, 0 is the easiest acceleration to work with. And so even though I'm doing it twice, this new time, the second time, this horizontal stuff is actually pretty easy. Because remember, 0 acceleration means don't change your speed. So if we started back here with a speed of 40, then a second later it has 40. Then 2 seconds it still has 40. 3 seconds it still has 40. 4 seconds it still has 40. 5 seconds it still has 40. And after 6 seconds, it still has 40. And so again, 0 acceleration means 0 change in speed. So whatever it starts at, it keeps going. And that's what I said over on the break. And then hopefully you see it here in this little animation. You'll see that if something had the same speed, it would always go the same distance every little measurement. And so these measurements would represent the same distance apart because they're the same speed. Which then makes this calculation not too difficult, but something that always has a speed of 40, we could very easily just say the average speed is 40. It started with 40, it ended at 40. You take 40 and 40, you add them together, divide by 2, you get 40. And so if it's always 40, its average is 40. So if I go 40 times 0 seconds, I get 0. That's where it starts. And 40 times 1 second is 40. And then, of course, 80, and then of course 120, and it just keeps increasing by 40 meters every second. Of course, that's what a speed, we said back in chapter 2, that's what a speed of 40 meters per second meant. 40 meters per second means go 40 meters every second. And so this thing is just going to increase by 40 meters. And so, again, a couple other questions that could have been asked with this problem might be something like, basically, where does it land? And so you figured out that it had a 0 height after 6 seconds, and then horizontally it's what I'd call downrange, 240 meters. And so this is where it lands. 240 meters downrange at a height of 0. Again, I suppose you could also ask, how far downrange is it when it's at its maximum height? Well, we concluded over here it had a speed of 0 at a height of 45 at 3 seconds, and downrange then would have been the 120. And so again, there's a whole slew of questions that could be asked. In fact, I would even say that if I didn't have to fill in the whole chart, like say on a test or a homework problem, I probably wouldn't do a whole chart here. I'm doing the whole chart to hopefully kind of get you to see that there's really a bunch of questions that could be asked for here. And if you just understand the physics, and I'll say it again, not new physics. And so this chapter, I hope, is coming across as an easy chapter because we're not really learning any new physics. So we're just back to chapter 2 and 3, just we're doing it twice. And that's what I want to keep saying here. All right, well, with all that said, there is, I think, a couple little minor things in the rest of this chapter that I should point out. A fun one to ask then is if you were throwing a baseball. Well, there I have a tennis ball. And let's say that no matter how I throw it, or excuse me, what angle I throw it at, so I could throw it at a 45 degree, I could throw it straight up, which I'll call 90 degree, or I could throw it horizontally, which I'll call 0 degrees. No matter how I throw it, let's just say I always throw it the same speed. So this might be a better description of a cannonball, because a cannonball gets fired by gunpowder. You load the gunpowder, and if you point it straight up, it goes a speed. You horizontal, same speed. 45, same speed. But here might be a good question. What angle would you fire it if you wanted it to go the maximum distance? And I hope you see something quite interesting here in this setup. Because when we were calculating distances, and now my question is maximum distance, I begin to see that the maximum distance is calculated with two factors. One is what is its speed, and this would be horizontal speed, and the other is the time. You see, what I'm getting at is your first reaction might be, oh, if you want it to go really far horizontally, then turn the cannon horizontally. Because let's just use the speed 50, like I was using here. If you were to fire this cannon at an angle that is something that's not 0, it would have a lower horizontal speed than the 50. So part of me says, hey, put it at horizontal, because then all the speed is horizontal. But the problem with that is, you don't have a vertical speed, it doesn't go in the air, it doesn't have much time, and so it's not going to go very far. Yeah, it's going very fast, but it doesn't have much time. So the other factor here is a lot of time. Okay, well, a lot of time. How would I get a lot of time? Well, that's the reverse of this. If you wanted this cannonball to spend a lot of time in the air, fire it straight up. You see, in this problem, the amount of time it spent in the air was 6 seconds. I'll just ask you a quick question. What if we were to fire the cannonball at 50 straight up? How much time would it spend in the air? And I'm hoping you're getting 10 seconds. And hopefully you would see it here. You would have started with a vertical speed of 50. And then you would have gone 50, 40, 30, 20, 10, 0. It would have taken 5 seconds to come to a stop. And then the reverse, another 5 seconds to come back down. And so if you want something with a lot of time, you fire it straight up. So that's what I should do for this cannonball, right? I should fire it straight up. Well, no, that doesn't work real well either, because although you get a lot of time, you don't get much speed. And so maybe it's not a surprise that the best way of getting a maximum distance is to balance those two. And those two get balanced at 45 degrees. In fact, we've got a nice little animation that shows this cannon. I'll turn it on. It starts right away, so after it does its thing, I'll restart it again so you can see it from the beginning. But it fires, I think, 6 different cannonballs, all with the same speed, but a slightly different angle. And it's right here. It's called projectile range. I'll click on it. 1, 2, 3, 4, 5, 6. Yeah, so it is 6 cannonballs. And to kind of, again, illustrate this, watch what's happening with these 6 cannonballs. The one at 15 degrees, look how fast it's going horizontally, but doesn't spend much time in the air. And so it lands right away and doesn't go very far. And then likewise, look at the one that was 90 degrees. It was in the air the most time. It went straight up, spent a lot of time in the air, what we'd call hang time in the air, and then came right back down. And that's the whole balancing effect here. And that's why the 45 went the most. And so I'll show it one more time. It all depends what you want. So if you want a big distance, 45 is your goal. On the other hand, you want a lot of time, then you got 90 degrees. And so it kind of depends as you do these problems. If they're asking you, you know, to hit a home run, well, to me, this is what you want, the maximum distance. That's what that problem is saying. Hey, take a baseball, hit a home run, it's 45 degrees. Now, by the way, I should probably point out, that is without considering the spin and the aerodynamics of the ball. Because I believe 35 is actually the best angle for a baseball when you throw in the spin and the air resistance. But for us, without all that effect, I'll say it's 45. On the other hand, there are other reasons. Let's take the game of football. Maybe you really aren't concerned about the whole distance. In fact, the whole distance may put it out of the field of play, so you don't punch the football at 45. Maybe the better punch is the 75 or even the 60. I'll go with the 75. The 75 will move it way down, so your opponent's going to have poor field position. But better still is it would take a lot of hang time, and that's even better to get your own players down there to make the tackle once they catch it. And so it depends what you want. I wouldn't think a punch that would straight up would be very good. I guess I can't even think of a good reason when you would want it to go straight up and straight down, but that would be your most hang time. And so that's one of the things that I wanted to point out. Let me point out a second little thing here as we wrap up this chapter. And that is, our objects aren't always these little points. What I mean by that is every time I've talked about an object, I've either thought of it as this like little point, or maybe just thought of it as a round object like this tennis ball we have here. The animation shows these round objects. But what if I don't have a round object? You know, what if I have an object like this hammer? Or I have an object sort of whatever you want to call this. This seems to have two spheres connected with a rod. And I were to toss them across the room. Would they make this parabola? And the answer is yes, but. Here's the but part of it. I'll put this one down because your author uses this as an opportunity to introduce you to the center of mass, although it is just an introduction. Let me emphasize that. We are going to talk very heavily about center of mass when we get to chapter 8. But for right now, you can't really completely understand this until you at least mention what we call the magical point. And the magical point is this center of mass that follows this parabola. That is, if I were to toss this hammer across the room, it would spin, and in our case, the magical point is right here. And what we mean by that is if you were to hold it at its magical point. Maybe I should have turned it to you. Right here, it's not the middle of the object. I want to emphasize that. But it is a nice combination of distance and weight. This side has a lot of distance and very little weight because it's made out of wood. This side of the hammer has a shorter distance. It's the head of the hammer, but it also has a lot of weight. And so those two balance each other somewhere, and that's called its center of mass. And so when we say we throw something, what we mean is its center of mass follows this parabola, where the rest of the object then rotates around it. And that's what chapter 8 is. Chapter 8 is about rotations, and that's why really the most discussion for this will take place in chapter 8. What you can see it here. That's why we put the string right about here. The string is tied at what we call the center of mass of this object. We have a bigger sphere and a smaller sphere. Notice the bigger one has a distance that is shorter than the lighter one. So if I take the mass of that one times this distance and the mass of this one times that distance, I get the same number. And so that's the center of mass. And so if I were to toss this thing across the room, what would happen is this point right here would follow the parabola. This point right here is the point that I am showing you how to calculate. The other stuff would rotate around it. And so like I said, it's a little premature to get too much into rotations. So more on that in chapter 8. But you can't really completely, I think, get the gist of projectiles, of odd-shaped objects, until you also point out the center of mass. And that's why I wanted to bring up your book here. And so let me come back over here and click on your book here. Your author does a good job on this page. Let me make it a little bigger here. And in this diagram, he has it looks like a crescent wrench. And the crescent wrench, he's just sliding across ice. And so the camera's up above looking down, and I don't have a crescent wrench, but I'll take my hammer because it's kind of the same idea. My apologies. Sound check. Am I back on? I bumped my cordless mic here and went all over the place. And so I think we lost sound there for a second. Sorry about that. All right, so my hammer cut it like this. All right, so but back to this hammer, which sort of looks like this crescent wrench here. But if you're the camera and you imagine yourself on the ceiling looking down, and I slide this on ice, as it slides, there's no force on it, so Newton's first law says an object in motion stays in motion at a constant speed. But the part of it that stays at a constant speed is the center of mass, and that's what they're trying to show. And so they've got a white dot, and so as the crescent wrench, and it looks like the crescent wrench is moving along and rotating, that spot right there, that center of mass remains the same here. And your author also has a picture of a projectile This is supposed to be this ballet dancer, and they show the ballet dancer photograph here. But down in this diagram, they're trying to show that the center of mass, which is about around the belly of the belly dancer, it goes up and then comes down. And so the center of mass does follow a projectile. In fact, this goes one step further, and it's showing how the artist can make it appear that they just are going up and straight and down, because as they adjust their arms, they adjust their center of mass, and they keep their head at about the same location. And so as they start their jump, they have their arms down, because their center of mass is supposed to be low. That essentially has their head up. And as they go up, they bring their arms up. That brings the center of mass up without making the head go up. And then as they begin to go down, they bring their arms down. And again, that keeps the head pretty much straight. So I want to keep emphasizing the head is not the center of mass. And the head does not follow a parabola. The center of mass follows the parabola. And there's nothing the ballet dancer can do about the physics of it. There's going to be a center of mass, and it's going to follow a parabola. The other parts don't have to follow a parabola. They're in relationship to the center of mass. But the center of mass must. And so that's why your author gets into center of mass and rotations a little bit earlier than I think he would like to, but I think it's necessary. So I'm kind of glad he touches on it, but I will say, I'll just leave it at that and say let's talk a lot more about center of mass and rotations when we get to chapter 8. And also, your author touches on one more thing that, again, he's going to expand on later on, and in this case, later on is the next chapter in chapter 5. So we'll get started with chapter 5 in a little bit here. But he says, how does an object orbit? How do we put up these satellites? Or for that matter, how does the moon then orbit the Earth? And so I've grabbed my little globe here, and what hopefully looks a little bit like a moon. And how does it work? And this was Newton's brilliance. He figured this out with projectile motion. Many people thought at Newton's time that, well, the moon is way out over there and there is no gravity there. And as we're going to see in the next chapter, there is gravity. Now, it's less than at the surface, okay, but there still is gravity. And so how come the satellites don't fall and hit the Earth? How come the moon doesn't fall and hit the Earth? How come the Earth doesn't fall and hit the sun? Is there not gravity from the sun? Oh yeah, there is. So how does it work? Well, your author has a picture of this, although I think I have a better animation, but I'll turn to your author's picture. I'm trying to remember where, oops, I think it's back up here. He pushes it. It's kind of a simple diagram. Here it is. It actually kind of looks like Newton's original diagram. Yeah, it is in Newton's book here, yeah. And so here's Newton's thinking. I'll draw what I'll call a bigger diagram here. And here's kind of Newton's thinking. He said, okay, let's take the Earth and let's put somebody on a hill. I'll call it a mound because it's not really that big of a hill. And let's put them on top of this mound and have them throw an object. It doesn't matter. I'll just call it a tennis ball since that's what I have here. So let me come over here and grab a tennis ball. And so if I come over here and pretend that, I'm this person on this mound and say, okay, I'm going to throw horizontally this tennis ball. So there it goes. So I throw the tennis ball. I throw it horizontally. But the real key is I am 5 meters above the ground. The combination of the mound and my own body height, I let it go 5 meters above the ground. And let's say at first I don't throw it very fast. Let's just say I throw it at 10 meters per second. How much time is the object in the air? Now I've erased it, but I hope you saw in the last two calculations we did, didn't an object fall 5 meters in 1 second? That's the reason I picked the 5 meters, because here's what I know. I know, because of the projectile motion, this is the whole point of today's lesson, is that the horizontal and the vertical act independent. And so whether I give it no horizontal speed, a small horizontal speed, or a big horizontal speed, its vertical speed starts with 0 and it will take 1 second to fall. So this object would look like that. And if I threw it a little faster at 20 meters per second, it would look like that. And if I threw it even faster at 30 meters per second, it would look like this. It would, in all three cases, it would be in the air for 1 second, because the vertical and horizontal are separate. Now, the one with the larger horizontal speed would go further horizontally. And so this one here is going to go further. I get that. But I want to convince you, and so here is Newton's argument, and Newton's really kind of the first one to discover this and figure out how the moon actually orbits the Earth, how the moons of Jupiter actually orbit Jupiter, how our planets orbit the sun. And he's the first one then to really understand it, and the first one then to say, hey, maybe we could make artificial satellites. Maybe we can make our own satellites someday. Because when we run the numbers, and Newton ran the numbers, you'll see that there was no technology